Okay, without further ado, I'm going to move to the first speaker this morning. And just before I introduce her properly, I just want to say these first two talks, you're going to see a lot of sort of optical and glass work and fibre work. And I want to remind you right from the outset that you have some pracs for those of you who are here on campus. You have some pracs which involve fibres. And those of you who have done them, you will see they're really cool pracs. So that's the connection for later when you get to do those, whether it's today or later in the week. Think back when you're doing the fibre work with Pete and with Nick, you can think back to some of the talks that you're going to see this morning. So that's that connection. The first speaker is Professor Heike Ebendorff-Heidepriem. She's at the Institute for Photonics and Advanced Sensing, IPAS, and that's where the facilities are based tonight that you're going to go at Adelaide Uni. And she's also part of the ARC Centre of Excellence for Nanoscale Biophotonics. And if you don't know about Centres of Excellence, that's a very prestigious, very large funding source in Australia. Heike received a PhD in chemistry. Fantastic, chemist, another chemist like me, but doing a lot of physics as well, I think, at the University of Vienna in Germany, and held 2 prestigious fellowships, as well as receiving the Weil International Glass Science Award in 2001. In 2001, Heike joined the Optoelectronics Research Centre at the University of Southampton, UK, before moving to Australia in 2005. Heike currently leads the Fibres and Photonics Materials Research Group at the University of Adelaide and is the Deputy Director of the Institute for Photonics and Advanced Sensing. Her research focuses on the development of novel optical glasses, fibres, surface functionalisation and sensing approaches. And on a personal note, really fantastic and interesting research. So we're looking forward to hearing from you, Heike. Let's make you feel welcome.
Thanks, Craig, for this fantastic introduction. And it's a great pleasure for me to be here and to show you everything about, or most about, specialty optical fibers. And let's see where I can grab my slides.
Sorry, Heike. My fault. It should be open already, right? Are your slides open? No. Okay. Just a second. Let's do... Where are they? Already open?
Yeah.
This one?
Yeah.
Okay. Yep. We'll go to screen slideshow. Oh, not.
So just jump back into...
To Zoom first.
Yeah. That's it. And then...
And we should be able to do that.
Okay, thanks, Craig. So as I said, yeah, it's a great pleasure to be here, and I welcome you here in this auditorium, and also welcome everybody online out there. So I will give you a little bit of insight in specialty optical glasses and fibers, their fabrication and applications. So first I would like to give you a little bit more insight on the landscape of ANFF. Most likely Craig talked about it. So currently we are here at the SA node of ANFF. And there's also the OptoFab node. And the OptoFab node has several locations. One location is Adelaide University. And there, the OptoFab facility at Adelaide University, we call ourselves OptoFab Adelaide Hub. And as Craig mentioned, this evening you have the opportunity to see our facilities with your own eyes this evening at 6 p.m. And there are still a few places left, so please come. And as Craig said, the important thing is first tours and then pizza. Okay, so the outline of my talk, 2/3 of my talk is about fabrication. So from glass, making the bulk glass, to making the preform with the macroscopic structures, and then to the fiber with a microscopic structure. And then the last third of my talk is giving 3 examples of applications for these fibers. So let's start with glass. First, glass composition. So if I say glass, I mean inorganic, non-metallic glasses, and they can be categorized into silica glass and multi-component glasses. So silica glass, the main component is the network former SiO2, And silica is used for the majority of optical fibers. And through the next slides, hopefully you will see why this is the case. Then on the other side, we have the multi-component glasses. They can be divided in terms of the network former component. So one are very well known are the oxide glasses. So we have a borate, aluminate, gallate, silicate, germanate, phosphate, and telluride are the main examples. Then another group of glasses are the fluoride glasses. And they are mainly composed of zirconium fluoride and indium fluoride. And the third group are the chalcogenide glasses. Their N-ions are the chalcogens, sulfur, selenium, and tellurium, and the corresponding cations are germanium and arsenic. And of these many glasses, some glasses that have a softening temperature lower than 700 degrees Celsius, they are called the so-called soft glasses, and typical examples are heavy metal oxide glasses like lead silicate, fluoride glasses, and chalcogenide glasses. And I also want to point out here these rare earth ions. They show luminescence, and therefore they are doped into glasses to create active glasses, for example, for laser applications. So this is on composition. So the next is now, as you can imagine, with many materials, you have composition, and they predict or determine the glass properties. So what I have done here is on the horizontal axis, I have the most important thermal property of a glass. Okay, got it?
Sorry, yeah, that's me.
The glass transition temperature. And roughly the glass transition temperature scales with the thermal, mechanical, and corrosion stability of a glass, and also with the melting temperature on the glass. And roughly it scales inversely with the infrared transmission. Then on the vertical axis, now it doesn't want to. Any idea what we can do?
Just use the arrows, maybe.
Okay. Yep. And so the refractive index roughly scales with optical nonlinearity. Yep, works. Great. Thanks, Craig. And what I've plotted here now are typical glass families, how they sit in terms of thermal properties versus optical properties. And let's have a closer look. First, silica on the right side. So it has the highest glass transition temperature. Therefore, you can imagine is the glass with the highest durability. On the other side, it has a low refractive index. What this means, one can transport high power without running into nonlinear effects. And so therefore, silica is perfectly suited for high power laser applications in the near infrared. Then on the left side, we have the chalcogenide and the fluoride glasses. So they have the infrared transmission. And the fluoride glass, again, have the low index combined with infrared transmission. Therefore, they are well suited for high-power lasers in the mid-infrared. The chalcogenide glasses, they have extremely high refractive index, therefore high optical nonlinearity, and so they are good for so-called nonlinear processing. That means creating new wavelengths, like from one laser, you pump the glass with one laser and you get a broad supercontinuum out of the fiber. In the middle, we have the heavy metal oxide glasses, telluride, lead silicate, lead germanate. So they have a really interesting combination of glass properties like low temperature processing, high crystallization stability, high rare earth solubility, high index, and that really makes them suitable for easy processing. And so we use them a lot for creating, investigating new sensing and other concepts. So this is on properties. So the next one is to make the glasses. And I list here the 4 main fabrication techniques I'm aware of. And the most widely used technique is the so-called melt-quench technique. So it's also used at OptoFab Adelaide. And as you will see in a second, with this technique, you can almost make any shape and size. And you are aware of glasses made via these techniques through window panes, household, and labware. So how it works is as follows. So you take crystalline raw materials, you mix them according to the recipe, you place the batch into a crucible, the crucible goes into a furnace, you heat it up, and all crystals at some point melt, and crystals that do not melt, that get dissolved in the hot glass melt. And so at some point after half an hour or even several hours, then all ingredients are in the molten state. Then you can cast the molten glass into a mold, as shown in the photograph. And now you can imagine the shape now depends on the size of your mold, and of course also on the volume of your glass. At the laboratory, we make small volumes in the order of 100, 300 milliliter, but you can imagine if you want to make window pane, then the volume of your glass then goes into the tons. And then once glass is cast, then it goes into an annealing furnace to then slowly cool down to room temperature to avoid that the glass cracks. Now at OptoFab Adelaide, we have furnaces that operate in ambient atmosphere, and we can go up to 1,400 degrees Celsius. But in particular for fluoride glasses and mid-infrared glasses, we have the facility to melt them in controlled atmosphere, where we can go up to 1,250 degrees Celsius. And so we can melt in a dry atmosphere, which is important to achieve mid-infrared transmission. So second technique for making glass is the chemical or physical vapor deposition, because in this case one starts with liquid raw materials, and therefore they can be provided in extremely high purity, and therefore this technique of deposition is extremely well suited for high purity applications, provides a limited thickness. The main example of how it's used are silica fiber preforms on a massive scale. So this is how the optical fibers are made that are then the undersea cables to transport our internet signals across the continents. Third example, it's a relatively new method, came up really in the last decade, is the nanoparticle sintering. Again, nanoparticles like silica nanoparticles can be made in high purity applications on high purity fashion. Again, there's some thickness limitation because the nanoparticle sintering has some shrinking involved, and this limits the thickness. Examples are again silica fiber preforms with larger cores, and in the last few years really more and more groups they explore 3D printing based on silica nanoparticles embedded in a resin. Fourth example is Sol Gel. It's a fantastic method for low temperature processing and making unusual glass compositions that can't be made with any of the other techniques. Again, there's a thickness limitation, and it's widely used for preparing glass coatings, and also the Sol Gel itself is used to make then the nanoparticles that then can be used in the nanoparticle sintering. So this table here gives you an overview of the different glasses and also polymer, as an example of organic glasses, we are using at OptoFab Adelaide. So we use a lot of commercial glasses, because if you need a certain glass property and it's available commercially, then we buy these glasses. But we also make a range of in-house glasses like zirconium indium fluoride glasses, telluride, germanate glasses. They are all the mid-infrared transmitting glasses. Then we use soda lime silicate glasses, for example, for investigation the precipitation of gold and silver nanoparticles for colored glass applications, and then a range of polymers. So this is all about glass, and before I come into preform and fiber manufacturing, just this slide about the two classes of fibers. One are the conventional step index solid fibers, where the core is made out of a glass with a higher index, and the cladding is made out of a glass with a lower refractive index. And on the other side, we have the microstructured fibers, where now regions of different refractive index are provided by having air holes in the fiber cross-sections, and these air holes run along the whole length of the fiber. So we make our fibers always in a two-step process. So first one makes a preform with a macroscopic structure, in our case in the order of 10 to 20 millimeter diameter, and this preform is then drawn down to the fiber, which has then a microscopic structure with outside diameter of 120 to 200 micrometers, so as thin as a human hair. So there are a lot of different fabrication techniques for making the preform. For making step index preform, the two main techniques are modified chemical vapor deposition for making silica preforms, and the casting techniques for making soft glass step index preform. So again, the deposition and the melt quenching techniques. Then there are the techniques stacking, drilling, and extrusion, and they are used for microstructured fibers, where one starts already with a made glass. And I will go through these three techniques. And within last 2 years, more, as I already mentioned, 3D printing has come up on the scene for making both solid and microstructured or preforms for microstructured fibers. There's still quite a lot of work to do to achieve sufficient optical quality. So watch this space. I'm very happy and glad to tell you that in 1 or 2 months we will get our own 3D glass printer based on filament printing, and we ordered sintering furnace, so in a few months' time we can also look into 3D printing of glass via the nanoparticle sintering technique. So watch this space. So I will now go through extrusion, drilling, and stacking, so the three main preform fabrication techniques we are using. So extrusion works like follows. So we either buy or we make our own in-house glass billet. This billet is placed on a so-called extrusion die, mostly made out of metals, and you see here the die exit structure, which then determines the structure of the preform. So the die exit is the negative of the preform, and via squeezing the glass through the die, we create then air holes all along the preform. And so this technique is perfectly suited for glasses or materials with low softening point, and therefore polymers and glasses with softening points below 1000 degrees Celsius. And it allows an almost unlimited range of structures, which you hopefully can see from the photographs of these preforms. Nice thing is also because the glass is hot when it comes out of the die, and therefore it fire polishes, creates a smooth surface, which is always important for optical properties. We can make very small features, 0.2 millimeter already in the preform, large aspect ratios, preforms with 20 millimeter outer diameter and 0.5 millimeter hole size. And in the last 2 years, we use more and more 3D metal printing to make our extrusion dies, so that we have access to new designs, but also new die materials. And so this really brings me to this slide. So we have a 3D metals printer, which we use for making our extrusion dies, but we use it also to make a lot of other things. And so we work with many industry companies together. And so our 3D metal printer works with the principle of selective laser melting of powder. We use mainly a titanium alloy. The geometrical position is 100 micrometer, that means 0.1 millimeter. That brings me to my next slide. The 0.1 millimeter, of course, precision is not enough if you want to make an extrusion die where we have slots of 0.3 millimeter. And so therefore, we also have a high precision 5-axis CNC. And so often we first make a part via 3D printing, and then it goes to our CNC, and then we fine machine it to achieve then the geometrical precision of 20 micrometer. So our CNC can be used for metals, glass, and polymer because we have an ultrasonic function. And so then we use it also for creating holes and slot into glasses, and this is another way of creating preforms with air holes. The third technique is the stacking technique, where mostly silica capillaries are taken, and they are stacked in a certain pattern. It works very well. Very complex structures can be made, as I have shown here for one example of fiber. So you can imagine the drawback, it's labor intensive and really needs a skilled operator. We had a few trials 1-2 years ago. You see here then the fiber made with this technique. And we did 3 to 4 trials, and to make a really good fiber, I heard you need to make 100 trials. So we are now looking into getting the funding so that we can also do 100 trials, and then also we can make these hollow core fibers via the stacking technique. So this was all about preform fabrication. Now I'm moving on to the fiber drawing. So there you see the preform inside a furnace, inside a hot zone. Only a short part of the preform is heated up. If the heat is going on for a few minutes, then the glass softens, gravity forms a neck down, and a drop is coming down, as is shown in this photograph. Then the fiber is placed onto a capstan or drum. Then the drum starts to rotate. The preform is moved slowly into the hot zone. So slowly, the glass moves slowly into the hot zone, fast out of the hot zone. And so we go from millimeter to micrometer scale. Because we are working with soft glass and silica, they have very different softening points, and therefore we have 2 draw towers, a soft glass draw tower 4 meter and silica draw tower 6 meter. So this evening at the North Terrace campus, we can show you the soft glass draw tower. The silica draw tower is on the Theberton location. So here, just to show you the very different structures that can be made with commercial silica and soft glass, with in-house made soft glasses, with polymers, using extrusion or using deposition techniques and using drilling. Just to show you the extremes that can be achieved. So here you see a fiber which contains in the core center a 10 nanometer hole. And on the other extreme, this fiber which contains a hole of 60 micrometer. Note that all fibers, they have roughly the outer diameter of 100 to 200 micrometer size, so that the fiber can be drawn in a continuous fashion, and also can be handled afterwards. So this now brings me to my second part of my talk, 3 applications, so chip lasered, colored glass, and fiber sensors. So first application, I've chosen an application which works with the glass, so where the glass directly can be used. And this is to use a femtosecond laser to write directly channel waveguides into the glass. And so this then creates a waveguide, which you can say the channel is a fiber embedded in a bulk. And this is a method to create really compact and robust waveguides. And you can see this here on the photograph. So the glass itself is even less than 1 centimeter, so it's really only a few millimeter. And so this work, we providing the glasses, and we work there mainly with Mick Whitford, now to show the next here, and with Dave Lancaster here at University of South Australia, and really started with working these 2 groups. And so first we started with using fluoride glass to create lasers in the mid-infrared region. So here, just as an example, thulium fluoride waveguide laser operating at 1.9 micrometer. And so this work started in Macquarie University. Now Dave Lancaster has built the femtosecond laser writing facility here at Uni-SA. And now also Dave Lancaster and others, they have found the startup company Redshift Photonics. So you see the logo there at the left bottom of the slide. And so now they're looking into the commercialization of the technique. So Dave and I, we also have in the last 2 years explored the use of other glasses, like germanate glasses that have been made at Optofab Adelaide. Next example, eco-friendly colored glass. So this is by chance, and I can tell you more in the break if you want to hear about serendipity in research. We invented a new method to create gold and silver nanoparticles in glass. And we realized that by chance we invented this method for telluride glass, but then we tested it for a lot of other glasses, and for almost all oxide glasses it works, and you can see there the different colors we can make. Then we then worked together with glass artists because it became apparent gold, silver, nanoparticles, different colors. Who needs different colors? Glass artists. And so as you see here, examples of glass art made with colored glass made at Optofab Adelaide. Another application we have been looking into is the screen printing, and here you see results, a QR code, and also some other printing. And here it's a similar story now together with the two other inventors and we have formed 1 year ago the startup company Easy Glass Technology, and now we are looking into commercialization of the technique. Next example is 2 examples on fiber sensing. First, magnetic field sensitive fiber. So the concept here is that diamond contains nitrogen vacancy centers. And these nitrogen vacancy centers, they're shown here. They show a fluorescence in the visible, and the brightness of this fluorescence is sensitive to magnetic fields. And so therefore, for remote sensing of magnetic fields, we want to take advantage of the light guidance in a fiber for the excitation of the NV centers in diamond particles, and also for collecting the sensitive fluorescence. And this is shown here, for example, in transmission. You have the green light for excitation, and then we would collect the red fluorescence on the other side of the fiber. And so therefore, you can imagine to do this, we need to get the diamond nano or microparticles into the glass core of the optical fibers. And so we started to do this. We used telluride glass, low melting glass, and therefore we thought it would help to make the particles survive when we put the particles into the hot glass melt. So we started with the melt doping, having the particles everywhere. It worked, and we could measure the magnetic field sensitivity, but it had 2 drawbacks. One was telluride glass is a fragile glass, and because we exposed the diamond to a low viscosity glass, a large portion of the diamond particles didn't survive. So therefore, last year we then came up with a new technique inspired by glass artists, where now we take a 1 millimeter glass rod, we coat it with, in this case, with microparticles, and this tiny rod is then placed into a tube, and then this rod in tube assembly is drawn down to fiber. And during fiber drawing, we have a higher glass viscosity, and the particles, we couldn't see any sign of damage of the microparticles of diamond. This technique also allowed us to move from telluride to lead silicate glasses, which are much more robust. And we were very happy, so we have a more robust technique of doping, but it also led to a 20 times higher sensitivity because we used micro diamond particles, which create then a higher localization, higher concentration of NV centers in one spot, and also because we localize the diamond particles only at the interface between an inner and outer region, we have less scattering of the fluorescence when it travels along the fiber. Last examples of applications are fiber sensing based on suspended and exposed core fibers. So suspended core fibers on the top, exposed core fiber at the bottom. They both work in the same principle. In the center you have this triangular shaped glass region. This is the core where the light is guided. And as shown on this image, part of the light guided along the glass core is situated outside of the glass in the air holes, and if you fill the air holes, then the light can interact with what is in the air holes, and this is used for the sensing. So we achieve light matter overlap. So therefore the air holes, they allow this access to the light, but it also they act as the sample chamber. As I said, we have the two types, suspended core with an enclosed core and the exposed core fiber, where one hole is open to the environment, so easy access to the core. Now we can make both fiber types with different hole and core sizes. And so the different core size, we can therefore control the light matter overlap. And with the different hole size, we can control how much analyte volume is needed or how long is the filling time. As now I think here on this slide, I already give an example of the many applications. So the glass itself is not sensitive. And so therefore we put the diamond particles into the glass. And so also for other sensing application, we need to find a way of functionalization of the fibers. The easy way is a sort of functionalization that is that we fill the fiber with a liquid which contains the analyte plus, for example, the fluorophore, which gives the functionality. Because it's so simple and easy, it's less for real-world sensing, but perfect for testing new concepts. For example, we tested how far can we go down in sensitivity, and so we could really monitor a single nanoparticles in a fiber. We could sense it. Other example is then to put chemical coatings directly on the fiber core, and these coatings are then specific and sensitive. A third example is nanostructuring, like writing gratings or other cavity structures, physical nanostructures into the fiber core. So I want very briefly one slide on pH sensing and one slide on temperature sensing, because the pH sensing is an example of a chemical coating. So we use silk as a biocompatible polymer. A fluorophore is embedded in this silk. The fluorophore is pH sensitive. Then, because it's a fiber sensor, it could be used in vivo in a living animal and measure the pH, and with giving the animal less oxygen, then what's happening that the blood acidifies, and this then could be measured via the pH value. So the pH is an indirect measure of the oxygen level in the body. High temperature sensors, so this is an example of nano or microstructuring. So we use a silica suspended core fiber, so only glass is used to make the fiber. We create with a femtosecond laser tiny air holes into the surface of the core, so again an air glass structure. So these holes, they act as a grating, and only a certain wavelength is back reflected, and the position of the or the wavelengths of the back reflected light is sensitive to temperature, because silica deformation point is 1300 degrees Celsius, so we can go up to this temperature. Break gratings are ideal to write several gratings in one fiber. Each break reflects a different wavelength, so we can measure temperature profiles. Silica fibers are robust, so the measurements can be done in a corrosive environment. So one sensor is now still in one newly built furnace in the zinc smelter in Port Pirie. And the two inventors, Stephen Warren Smith and Eric Schardner, they founded their own startup company, HT Sensing. So hopefully also with these startup companies, I could give you an example of the translation of the research that has been done at OptoFab Adelaide. And I don't go through this, you can read it yourself. So OptoFab Adelaide provides various glass types, fiber structures, and functionalization methods. This gives many glass and fiber properties, therefore diverse functionalities and wide range of applications. And of course, the work I presented you has been only possible through collaborations of OptoFab Adelaide with many colleagues, collaborators, students, technicians from many universities in Australia, but also worldwide. And we would like to thank our many funding agencies and sponsors, industry, government, DSTG, also ANFF, NCRES, and so on. And of course, the most important people to be able to do all this exciting work are the technical staff at OptoFab Adelaide, and I really want to give them a very special thanks. Thank you for your attention. I'm happy to answer a question if there's time. I'm definitely around during the morning break to answer questions.
Thank you so much, Heike, for a wonderful talk and so many different glasses and applications, and yeah, it's just amazing. Are there any questions for Heike? We can sneak in a question. Belle, you keep an eye online for me. Yes?
Just noticing the air holes and the geometry is always symmetric to graded. Is there any advantage to just shifting it off the center?
Yes, and we have done this for the exposed core fiber, where we completely shifted it to the surface, so that also the access is easier. And this is an interesting example, because what we found is the fiber is fine, you can work with it, but because it's off-axis, often to integrate a sensing fiber with standard fibers, the telecom fibers, where the core is in the center, then it's not good to have an off-center core. That was the only reason for us now to make only exposed core fibers, where now the core is aligned in the center so that we can splice it to telecom fibers. What we also have done is making structures where at least you have one asymmetry, is not perfectly radial symmetric, to create then what we call birefringence into the optical properties, because usually if you guide light you have so-called two polarizations. So easiest is to think of one vertical, one horizontal, and they usually mix and with each other. But if you really want, you only go with one polarization in the fiber and you want to maintain it, then you create some asymmetry in the fiber so that then this can't mix with this polarization.
Okay, from Eyebrow Communication, I think there's something online, so Belle?
For biomolecule sensing and plasmonics, are there any novel glasses being used to increase the sensitivity of the sensor?
No, so we completely rely on coatings. What I'm aware of is that there's a group in Italy. They make biodegradable glass, and so then they use then this glass to make fibers. The fibers are used in vivo for sensing, but they only are in the body for a certain time period, and when the sensing is not needed anymore, the glass completely and safely dissolves in the body. So if someone is interested there, I'm sure you find the work of this group. It's very interesting.
That's amazing work. I'm going to wrap that discussion there and invite you to thank Heike. I'm just going to give you, Heike, a little gift.
great.
volunteering a bit of time for us. Yeah, a wonderful talk, and please talk to Heike in the morning tea break. Yeah.
And do I have timing information on there? No. Okay, I guess that much.
Is it already open for you?
Oh gosh, sorry.
It's all right.
I was talking amongst yourselves.
Sorry.
We're getting used to this, aren't we?
It's
Is there any of
test.
these? Is it that one?
That's it.
That's
Yep.
it.
Just go
okay.
back to the.
Yeah, we'll hang on. Just go to start from the beginning.
Can you just, no, I was going to say, can you shut off my email, because that's what's,
Is that what's going on?
yeah. Sorry, that's what's, so,
This one.
yeah.
All good?
Make sure my notes. That's
What's happened? Okay.
Did we miss?
it's my jokes that I've written there.
Oh, I need to go. Oh, really? Hang on. Sorry. We can
Are
share
you in?
now. Yeah, we'll go as fast as we can.
There you go, thank you. All
All
right.
right, but we
We're
got
good.
it.
Ooh, that was interesting.
There we go. Okay.
Okay,
It
now,
took 3 of us to do it. Is it?
all right, now I'm just going to pause the recording. What's it going to, oh, that's all right, I'll fix it afterwards.
Let me introduce you, Scott. So I really appreciate Scott joining us. He's done this a few years in a row and comes to us from the Defence Science and Technology Group. He's based out of Edinburgh here in South Australia. Dr. Scott Foster here has been a research scientist, or he started out as a research scientist in 1999 at DST. And since 2003, he has led research in novel undersea sensor technology based on miniature fibre lasers and worked in partnership with the defence industry to develop advanced fibre optic sonar systems. He currently leads the Next Generation Technology Fund Advanced Sensors program. He holds 3 patents, has 50 papers, many citations, and has contributed important works on distributed feedback fibre lasers and on the fundamental noise limits of fibre optic measurement. All things I don't know anything about, but Scott is the expert. His research interests include fibre optic sensors, advanced sensor materials, fibre lasers, laser noise, advanced interferometry, acoustics, and magnetometry. You can see that this is a perfect follow-up from the talk we've just had from Heike. Heike talked to us about putting fibres into animals and smelters and other things, and she mentioned some undersea communication fibres, but I think you're going to get a whole different perspective on what fibres can do under the ocean. Thank you very much, Scott. Let's make you feel welcome.
Okay, thanks, Fran. Should that little? Oh, is that for the online Zoom?
We can minimise it if you
Okay,
want.
it's okay. It was just.
It's annoying you.
I was just going.
I think we're okay.
Okay, so that image that you can see on the right-hand side of the screen there is an advanced ultra-thin or ultralight fibre optic sonar array, just drifting very gently to the bottom of the Gulf St Vincent, and I'm going to say quite a bit more about that later. But I just thought that I'd just start with a bit of a quiz. Can anyone guess which of the 4 images on this slide shows a sensor system? Okay, so I'll give you a few seconds to think about that, and then I'll answer for you. If you guessed, if you guessed the submarine on the bottom right-hand side, you would have been correct. So the 3 lumps on the side of that US submarine are a advanced acoustic sensor array or sonar, and that particular system is one of the most advanced sensor systems of its kind in the world. But I'm actually more interested in what's shown in the other 3 drawings, because each one of those illustrate or encapsulate not so much a sensor per se, but the potential for a future sensor. So Heike has already talked about the potential for diamond in precision magnetometry, and I like to think that beautiful red colour of that diamond there is due to nitrogen vacancy centres. And I imagine that if you expose that diamond to a magnetic field, that colour would subtly change. And if only we can be clever enough to be able to measure and monitor those changes in the colour of that diamond, then we would have ourselves a magnetometer. Right now it's a pretty stone, but it's the potential of a sensor. So those more mundane looking yellow crystals on the right hand side are an advanced ferroelectric material called PIN-PMNPT. So I'm spelling it out because if I actually gave the full name, it's literally unpronounceable. But its claim to fame is that it has the highest, or among the highest, piezoelectric properties of any material that we know of. And the reason that's important is because almost every sonar ever made for military applications is based on the piezoelectric effect. And so when new materials come along that are potentially 10 times higher piezoelectric properties than traditional piezoelectric materials, that's potentially a really big deal. And down in the bottom left-hand corner, of course, we have optical fibre, which enables us to pass precise information over hundreds of kilometres, possibly thousands of kilometres. And that particular photo there is actually an optical fibre laser, which is my particular area of expertise. And I'll say a bit more about that in a little while. But I should explain why advanced sensors are important for undersea warfare. They're important because submarines really don't want to be seen. And so in what's called anti-submarine warfare, basically it really demands the most advanced sensor technologies. And in that game, the submarine has all of the advantages because it's able to hide underwater. But it does have vulnerabilities. So submarines are very big, and they're made, generally speaking, they're made of steel. And as they move, they actually distort the Earth's magnetic field. And so using sensitive magnetometers, maybe Heike's diamonds one day, you can actually detect the effect of a submarine. You can actually see a submarine as it passes by. The other thing it's kind of obvious is that they make noise, right? They have engines. In fact, they have most superpowered submarines have nuclear reactors, and they make a noise, and so they're vulnerable to detection by acoustic sensors. There are actually arrays of acoustic sensors called sonars, and in fact, by actually stringing lots of acoustic sensors together, you can actually detect the sound of a submarine even when that sound is quieter than the actual noise in the ocean, like the sounds of the fish. And in fact, during the Cold War, allegedly, the US, using huge sonar arrays, were actually able to see Soviet submarines on the other side of the Atlantic. And so, acoustic sensors or hydrophones, so a hydrophone is an underwater microphone, are particularly important because sonar is actually the technology that the submarines themselves use in order to sense their environment, because the submarine can't see underwater any better than the people trying to look for the submarine. So the submarines rely on sound as well. So in some respects, what's called undersea warfare is absolutely underpinned by acoustic sensors, underwater microphones called hydrophones. And so what's really remarkable is that it's all based on the unique properties of one remarkable material called lead zirconate titanate, or PZT. So you'll know it from the starters in your gas stove. You know, click, click, click. You get a spark. So this material it's a ceramic that has a property called giant piezo. It's a ferroelectric ceramic which has a property called giant piezoelectricity. And so it's essentially an alloy. I'm not exactly sure what the technical whether it's an alloy or a mixture, but it's an alloy of two perovskites, lead titanate and lead zirconate. And in their pure form, both of these materials, they're chemically very similar, but they both prefer a different crystal phase, or they don't at room temperature. They both prefer to live in a different crystal state. And when you mix them together, and when you get that mixture at about 50-50, the actual crystal lattice doesn't quite know which crystal structure it wants to be in, and so the material becomes kind of unstable. It's called a morphotrophic phase boundary. And so the way in which that manifests physically is that when you deform the material, all the crystal, because the crystal structure is a little bit unstable, all the alignment of the molecules kind of changes slightly, and that manifests as an electrical polarization, or as we like to say, a voltage. When you squeeze it, you get a voltage. That's why you can use it to get a spark to start gas stoves. And almost every hydrophone ever made for the last 60 years has been based on this one material. And what's really exciting is over the last decade or so, there's these new materials, like those crystals that I showed you a couple of slides ago, which actually have even higher piezoelectric properties, about 10 times higher than this PZT, these traditional PZT materials. And so it's really exciting to imagine, well, what are the implications for the next generation of acoustic hydrophones in 10 years or 20 years or 30 years down the track. But there's more than one way to skin a cat. And the way that I like to detect sound underwater is using tiny lasers inside optical fibres. So because this is ANFF, I'm going to explain how these devices are made, just very briefly, or we're going to have a crack at it. So first you need to start off with silica optical fibre that's been doped with germanium to make it photosensitive, and with erbium, or a rare earth, and in our case erbium, in order to what we call activate it. So when you expose photosensitive silica glass or to high intensity UV, you can change its refractive index permanently. And so that allows you to actually basically to write these beautiful periodic structures into the core of the optical fibre. It's called a fibre Bragg grating. I think Heike briefly touched on some work that they're doing on fibre Bragg gratings. And if you then take a fibre Bragg grating and you put a defect right in the centre of it, what you create is something called an optical cavity. An optical cavity is a region of space that traps light. But it doesn't just trap all light. It traps light that is resonant with the optical cavity. So the way I like to think about it is that you have two mirrors, and if the light exactly fits between the two mirrors, so what we would say if the light is a harmonic of the two mirrors, then you have a resonance. And in that case, you have this intense trapping where the light is trapped within the optical cavity. It's kind of like a musical instrument, right? Like an organ pipe or a guitar string. So think of the harmonics. So the harmonics of the optical cavity, or the resonances of the optical cavity, are like the harmonics of a guitar string or the notes of the guitar, but they're notes of colour. So okay, so that's the first part of making a fibre laser is writing a fibre Bragg grating and creating an optical fibre inside. An optical cavity inside the optical fibre. But you need to get light in there. And that's where the erbium comes in. So what we do is we optically pump the erbium by sending a particular wavelength of light down the optical fibre into the cavity, which is absorbed by the erbium ions. Those erbium ions become excited and they start to glow or fluoresce. And those fluorescing erbium ions inject light into that optical cavity. And just one wavelength of that light, so you can imagine the erbium ions, they're fluorescing away, they're creating lots of light, right? They're glowing, so the whole thing is glowing, right? But it's all happening inside the optical cavity. And so the light at one particular wavelength, which is harmonic of that optical cavity, which is what I've tried to draw in that cartoon at the bottom, just fits into the optical cavity, gets amplified, and it builds up and it builds up, and it basically it flows out, and what you end up with is a laser producing light at a single cavity, at a single colour. So it's like a beautiful musical instrument producing a pure tone. And that's a distributed feedback fibre laser. So what's that got to do with sensing, right? Well, remember that the colour or the frequency of the light that this laser is producing is very pure, and that frequency is determined by that resonance condition, by the length of that optical cavity, by that harmonic condition of the optical cavity. And so what that means is that the frequency of the light is actually encoding the length of that cavity. And and just using the musical analogy again, as any musician knows, when the environment changes, the instrument goes out of tune. So when you stretch that optical fibre, the length of that cavity changes, the wavelength of the light changes. And so basically by monitoring the frequency of the laser light, you can actually, what you're in effect doing is monitoring the length of that of that optical cavity, which is a physical length. But remember that all of that magic is occurring inside an optical fibre. And so what that means in effect is that you can actually put that little device, that optical fibre laser, at the bottom of the ocean. And you can pump it optically over miles and miles and miles of optical fibre. And then you can read out the wavelength of the laser that the laser itself is producing over that same optical fibre. And so by monitoring changes in optical fibre, the changes in laser frequency coming out of an optical fibre, what you're actually doing is monitoring the length of a tiny little optical cavity miles and miles and miles away. And it turns out that this turns out to be the most precise way of measuring strain in optical fibre that we know. And I'm going to try to explain how sensitive it is. Right? So the frequency of the light remember, the frequency of the light is locked to the length of the optical cavity, right? Or to the resonance of the optical cavity. So if you imagine at any particular instant in time, the laser has one colour, just has one frequency. But that frequency is not stable, it's changing over time, right? And so that smears out the frequency over time, and so you get a finite line width. But let's imagine that we are actually continuously measuring the frequency of the laser. Then what we're measuring is a sort of a time series. And that time series is going to look random, it's going to look like noise, and we call that frequency noise. And so what this plot here is a plot of the spectrum, so that is the Fourier transform, of the frequency noise, right? So on the x-axis we've got the fluctuation frequency, and on the y-axis we've got basically the size of the wobble, right? But because we can identify the frequency of the laser with the length of the optical cavity, we can relate this frequency noise to an equivalent strain noise. So if I wanted to know what's the minimum possible strain that I could measure at any given dynamic straining frequency, all I need to do is, let's say that I was straining the laser at 1 kilohertz, right? So I was wobbling it at 1 kilohertz. So I come across here to 1... Hang on, how do I do this? I need to use the pointer for this. Okay, that's not working, so can I use the mouse? Yeah, okay, so I come across here, so 1 kilohertz on this graph. I go up here to where this noise limit is, right? So I obviously can't measure it if it's less than the noise. So I can measure any signal that's higher than that. Come across here, 10 to the minus 13. So my strain resolution is 1 part in 10 to the 13. So I'll say that again. 1 part in 1/10 of a trillion. Okay, that's really, really small. So what makes it even more remarkable is that black curve. So what that black curve is, I've actually calculated what the thermodynamic fluctuations of the length of the optical fibre actually are. So that's actually a fundamental limit on the actual precision with which you can measure the length of optical fibre in principle. And obviously you can see that black curve sits right over the top of my frequency noise curve. And so what that's telling me, maybe you have to take my word for it, because I understand this is sort of hard to understand, is that's telling me that not only are these fibre laser sensors able to measure strain very precisely in practice, they're actually able to measure strain as precisely as it is possible to measure strain in optical fibre in principle. And they all do it inside the optical fibre, miles and miles away if you want. But hydrophones don't measure strain. Having the most sensitive strain sensor is really only the start of the story. You then need to and I suppose that was probably the point that I was trying to make on my first slide, you then need to harness that intrinsic property of this device and turn it into something useful. And so hydrophones basically measure pressure. And so all of our hydrophones are based on a flexural beam. And you can think of it as like a little machine that converts pressure to strain, okay? So pressure acts on a beam, it deforms the beam. The laser sensor is bonded to one edge of the beam, and so when the pressure deforms the beam, that stretches the fibre laser. Fibre lasers are really good at measuring strain, or stretching, if you like. And there you have it, right? And all of our sensors, and it turns out that you can actually, by playing around with the properties of the beam, you can actually engineer the properties of the sensor, and that's what's important. And we actually use, all of our sensors are made with silicon, well, most of them, because that has the material properties of the silicon turn out to be really good for acoustic sensing for reasons I won't go into. So all of the ones shown here on this plot here have all been made with a wet etching technique, KOH etching, and you can see the beam here has sort of been, you can see that's the beam there, you can see where it's been etched into the silicon. You can see here the fibre laser actually bonded to that. In this case, the fibre laser, which glows green, has been bonded to the outside of the beam, and so that's our little acoustic device. And if you don't believe it, that's a sensor.
Okay, this recording is taken on Monday, the 21st of March, 2011. Right now, I'm standing about half a metre, I guess, from the hydrophone. What I'm going to do now is I'm going to walk away towards the door and I'm going to talk again some more. Okay, so now I'm about 4 or 5 metres away from the hydrophone, walking away. Okay, now I'm at the door to the fibre optic slope.
I've really got to update that recording because it's getting a bit old. But I've got some much more recent ones. I've got one from last Christmas where I was singing "O Come Ye Merry Gentlemen" into a fibre laser hydrophone over 100 kilometres of optical fibre. So but next year I'll put that one in. So that's all being done just by essentially measuring the wavelength or the frequency of light coming out of the optical fibre. I still find it remarkable. It still blows me away every time I hear that. But that's still only just the beginning. Because you then need to take that. I mean, you know, it's nice if you can write a nice paper and it's impressive and it's fun, but you then need to take undersea sensing is a very demanding application because the ocean is a very demanding environment. So you then need to take those sensors and you have to integrate them into a sonar array. And sonar arrays aren't just one sensor either. Sonar arrays, generally speaking, have very, very large numbers of sensors. And this is the ultralight. This is our fibre optic seabed. This is an example of a sensor that we built a few years ago, basically in order to demonstrate our hydrophone technology at sea. And I just want to point out a couple of just properties which I think are really interesting. So these silver blobs that you can see right in the middle of the screen, each of them is a fibre laser hydrophone. So each of them has one of those little silicon structures inside of them, and each of those little silicon structures has a little fibre laser bonded to it. And each one has been designed. Remember that the wavelength of the laser depends on the length of an optical cavity, which is determined by the properties of a fibre Bragg grating. So each one has been engineered to produce light at a slightly different wavelength. And so we actually have 8 sensors here, but they're all on one optical fibre. And so so what we do is we send our pump energy down the optical fibre, and you can see that yellow cable at the front. That's part of our 4 kilometres of lead-in cable. So we send our pump energy down there. It's just one optical fibre. It energises each of the little lasers in series. Each of those little lasers produces its own light, sends it back down the same optical fibre, same 4 kilometres of optical fibre. And so there we have, and at the other end we have 4 different wavelengths that we can then just read off, and we can read off our sensor array. And so this entire thing, all 4 kilometres of it, weighed less than 20 kilometres, less than 20 kilograms, and most of that was actually the 4 kilometres of lead-in cable. It's remarkably, and the stowage volume of it was, I think it was like a quarter of a cubic metre or something. And so that's really unprecedented for sonar. So for traditional sonar, you just simply couldn't do it that small. And we could scale this up to 100 kilometres or more potentially. So I can't resist just playing some sound. You're probably wondering what it sounds like down there, right? So this is another recording I just love, and I always play it. So that's our trials vessel. So it was about half a kilometre away, and it's just sitting there idling. So the captain's going to cut the engines in a second, and it'll go quiet. So you'll hear what it sounds like right out in the middle of the Gulf. Okay, there it is. Isn't that peaceful? Now, so you can hear that crackling sound. So you're probably thinking that that's electrical noise, but it's not. And I'll explain what it is. I'll explain why we know that it's not and what it is. So basically, so what you're just listening to is a single hydrophone. We actually had 8 hydrophones, and we had them all laid out at known distances. And so what that allowed us to do is do what's called array processing or beamforming. And when you do that, you get an image, you get this beautiful underwater soundscape like what's shown here on the left-hand side of this screen. And so each different acoustic, so it basically you can think of it like a decomposition. So you know, like when you take a Fourier transform of a time series, you sort of decompose into the different frequencies. Well, here you're kind of doing a two-dimensional, because you've got space as well as time, you're decomposing into both space and time frequencies, and so you get like a two-dimensional image. It's quite beautiful, and what it does is it explodes each different independent source of sound into a different blob of colour. And so you can get, this is incredibly rich in information. So firstly, electrical noise, I know that electrical noise shows up as a straight line right down the centre. So there's nothing there. So we know that there's no electrical noise in that signal that we're listening to. I also know that this line here, this is our trials vessel. And I should say that this is a snapshot that was taken after the captain shut down the engines. And so this is actually taken when we couldn't actually perceive the sound of the boat. The reason I know it's the boat is because all these, you see these thin lines in frequency, they're called tonals, and that's mechanical. That's the signature of mechanical noise. So we know that this is mechanical noise, and also know where our ship was. And so I know that is the ship, but I also know that we're actually listening to the ship in a region where the noise of the ship is actually quieter than the ambient noise in the ocean. And we're able to do that because we're looking at lots of different we're looking at data from multiple hydrophones coherently. So then we get this big smear of energy up here, and that's that crackling sound. And we know just from the properties of it what it is, and it's actually shrimp. It's actually marine crustacean. So what you were actually listening to when you were listening to that recording, it was going crackle, crackle, crackle. You were actually listening to shrimp in the mangroves north of Adelaide. So that's what it sounds like on the bottom of Gulf St Vincent. I'm just thinking, how are we going? We're a bit over time, aren't we? What? Should we just keep going? Okay, so I'm just drawing. This is a cartoon of our array, of our seabed array, sitting on the sea floor, and you've got all these hydrophones. There's a submarine that we're sort of covertly listening for. Well, I mentioned that submarines are also vulnerable to being detection by magnetometers. So what it would be really nice is to be able, instead of just having hydrophones down there, to also have magnetic field sensors, right? And to incorporate everything together into some amazing, what's called multi-influence detection system. So, if the submarine is particularly quiet, it might be magnetically noisy. If it's particularly magnetically quiet, it might be acoustically noisy. You're trying to maximise your chance of seeing the submarines, because like I say, the submarine has all the advantages. The problem is this is an optical fibre platform, and optical fibre sensors, generally speaking, almost all optical fibre sensors are strain sensors. And so that's good when you want to detect sound, because sound, converting pressure and strain are closely related, right? So it turns out that there is an effect, right, which couples, which it turns out that you can actually functionalise a strain sensor as a magnetic field sensor using a phenomenon called magnetostriction. And it's a property that certain materials have where they deform under it's kind of like the piezoelectric effect, but it's a magnetic analogue. So certain materials in the presence of a magnetic field, they deform. And it turns out that the deformation or the strain that they experience is directly proportional to the magnetisation of the material. So magnetisation, what's that? So magnetisation is basically magnetic materials. When you expose them to an external magnetic field, they become magnetised, and the amount that they become magnetised is called their magnetisation. So this is a material called terphenol D, which is an iron terbium dysprosium alloy, right? And this red curve is showing its magnetisation as a function of applied magnetic field. So the point is, you have strain which is proportional to magnetisation. Magnetisation is proportional to applied magnetic field. Therefore, you can measure applied magnetic field. I've tried to just draw it, but it's quite, as you can see from these curves, they're not linear, right? So you end up with quite complicated effect. But it's been there's quite a bit of literature on fibre optic magnetometers based on magnetostrictive effects over the years, and very early work was done by the US Navy back in the 80s and 90s on fibre optic magnetometers based on magnetostriction. And these devices were kind of interesting and they kind of worked. They didn't work all that well and they were very complex, and so they were kind of forgotten. Then quite recently these new materials, and I mentioned terphenol D, this terbium dysprosium material, have renewed interest in magnetostriction for optical sensors because they have very, very, very high magnetostrictive coefficients. And so there was some work about 10 years ago where people were coating Bragg grating sensors with magnetostrictive materials, and they actually showed that they could get a strain of about 1 microstrain per millitesla. Well, that was what was reported in the literature. Some of our colleagues at the University of Queensland have taken it one step further, and they're working with very, very beautiful, precise sensors called cavity optomechanical resonators, and I've got a photo of one there. And you notice it's a bit shiny on top, so that's actually been coated with terphenol D by us out at DSTG as part of a collaboration with them, and it's been functionalised, so it's a tiny little magnetic resonator, or magneto-optical resonator, and it's been functionalised as a magnetometer by coating it with this magnetic material. And so my idea was basically to take one of our fibre laser sensors, coat it with terphenol D or some magnetostrictive material, and in principle have a very, very sensitive magnetometer. So essentially you're functionalising what is the most sensitive fibre optic strain sensor as hopefully the most sensitive fibre optic magnetometer, right? And so I've just got some nice images of I believe this is terphenol D. Terphenol D coating optical fibre, and you can see the nice thin layers of around about a micron thick. And so I did some calculations based on what was published in the literature for the amount of strain that you get on the amount of wavelength shift you get in conventional Bragg grating sensors. And I sort of predicted, based on what I know from the minimum detectable strain of fibre laser sensors, that I would be able to get, say at 1 kilohertz, a magnetic sensitivity of about 10 to the minus 10 Tesla, 100 picotesla, which is actually quite good in getting into a regime which is actually useful for detecting submarines. But when we actually did the experiment, we were about 100 times less sensitive than that. And the reason for that, and that, believe it or not, that's still among the most sensitive fibre optic magnetometers ever made. And the reason is because optical fibre is historically not very good at detecting magnetic fields. But for us, it's just nowhere near sensitive enough. And so what we've been doing since then is we've been investing a lot of effort into actually understanding and optimising magnetic materials. And so what this thing here is called a vibrating sample magnetometer, or VSM. And it's basically the machine that you use to measure these kinds of curves, hysteresis curves. You've probably seen them in textbooks, right? And this gives us a huge amount of, this tells us not only how the magnetization behaves in the presence of a magnetic field, but also how you can actually control that magnetization, and how it depends on the history of the magnetic field that it's been exposed to in the past. And based on this information, for example, we can extract information that is very, very useful for optimizing a magnetic field sensor. I'm just looking at that and I'm thinking how long it's going to take me to explain it. And I don't think I'm going to have time, so yeah. And so I just want to finish off back with some of Heike's work and her collaborators, and just back with this diamond where I kind of started. And I just want to say that, so what I've been talking about in my previous couple of slides is taking what is essentially a fibre optic strain sensor and functionalising it as a magnetometer. One of our dreams over many, many years is to come up with an optical fibre sensor which is intrinsically sensitive to magnetic fields. And basically putting diamond in optical fibre and diamonds which are intrinsically sensitive to magnetic fields is one approach to doing, a very promising approach to doing that. So I don't need to say anything more about that because Heike's already covered it. So thank you. Sorry for going a bit over time.
Really fascinating presentation. I do want to allow a question quickly, if that's possible. Does anyone have a question for Scott? No? Okay. Is there anything online there, Bill?
Okay,
No,
everyone's
okay.
like splits, yes,
right,
yeah,
well-
yeah, so I'll be around for morning tea, so yeah, come and
Grab Scott
What's
over
left of
morning
it.
tea and ask him all your questions then.